Hi, I'm Martin. Designing human-AI interaction for the clinical domain can be challenging due to the safety-critical nature of the work and the probabilistic nature of AI models. Today I'll present an AI-powered visual search tool that can support pathologists in assessing cancer. Specifically, we aim to support finding cancer in colorectal lymph nodes. These lymph nodes are removed as part of surgically removing a cancer. In around 30% of cases, the cancer could have spread from the primary tumor to the lymph nodes and through them to the rest of the body. So if the cancer is seen in the lymph nodes, the patients will receive chemotherapy. That could mean the difference between living or dying. The method we used when designing an AI assistant for this task was basically a user-centered design process. We did fieldwork, built a predictive model, and we constantly evolved the prototype using feedback from pathologists during roughly an 8-month period. Following this, we performed a larger user study, which I'll present later. In order to design a successful human-AI interaction, we needed a realistic AI model. We collected the training data and trained a pretty standard convolutional neural network. The output of the model is a probability for cancer in each pixel of the image. To get a value for sections, we simply take the max value in each section. Compared to the state-of-the-art, we achieved a similar performance. But how good is that compared to pathologists? From similar works, we expect pathologists to be much better than our model. So while capable, using this model without a human in the loop is not an option. So how can we build a user interface that provides value despite the imperfect model? Let's first state our design goal. Our goal was to improve quality and/or speed of reviewing lymph nodes. In order to understand the way we did this, let's first look at how a manual review is done. These lymph node images are actually gigapixel sized and navigated using a zoomable user interface. Smaller cancers are only visible in high magnification. Therefore, concluding absence is the most time-consuming, as you need to search all of the tissue before deciding that there is nothing. In addition, most lymph node sections are negative. So again, how can we exploit the imperfect model to improve this search task? Let me describe the overall strategy that we used. So when you have a binary model, you can decide whether you want to be specific or sensitive. We select the threshold in order to be 100% sensitive. This leaves a lot of work with rejecting false positives to the pathologist. The benefit is that when all regions have been rejected, you can conclude that the section is normal without doing that systematic search. The challenges with that approach is that the review of potential regions needs to be very fast to compete with manual review. And we need to be careful not to bias decisions. Additionally, the user needs to trust the system in order to not perform a systematic review after reviewing the suggested regions. So let's look at the user interface we designed and how we handle these specific challenges. Let's start with an overview and then I'll go into the challenges. To the left is an overview of all the sections in a case with 4 suggested regions per section. It's always a fixed number and I'll go into why soon. To the right is a zoomable user interface, again showing the 4 regions in a low contrast color. In the top left, the positive and negative findings are counted, and this count is what the pathologist needs to put in their final report after going through the entire case. For being fast, we borrowed the RSVP technique and automated navigation. The only thing the user needs to do is indicate whether they see cancer or not, and navigation follows. We know that AI advice can cause confirmation bias. So this is why there are no labels or color coding indicating whether the model believes the region is positive or not. Additionally, always showing a fixed number of regions is also to avoid bias. For each section, we select the top candidate regions without applying any kind of threshold for regions close to 0. This was because we didn't want to implicitly bias the user through the non-presence of regions. Why 4? Well, that was a number that yielded 100% sensitivity on our test set. Since we're using a 100% sensitive model, the idea is that once you checked 4 regions, there is no need for systematic search. However, users might not trust us on this, and that is fine, and we should design for that. We did a couple of things. First, manual navigation is always available, and you can just ignore the regions if you want to. As an alternative, you can go through the case once and then increase the sensitivity to do 4 more regions per negative or preliminary negative section. Finally, while those alternative options are available, we designed the flow so if you just go with the flow, you'll always use the recommended strategy. For our evaluation, we wanted to know the effects on quality and speed of using our interface compared to the manual unassisted task. We had 6 pathologists review sections with and without AI support in a within subject design using a washout period. After the experiment, we conducted interviews in order to learn about the user experience. I'll be quite brief with results, and you can find more details in the paper. In terms of quality, the conditions were roughly equal, with a slightly higher sensitivity in the assisted condition. Using our system was significantly faster than the manual condition. For the average case, the speed up corresponds to completing the task in 6 minutes instead of 70 minutes for one case. One pretty serious drawback was that users struggled with identifying what might be an indication that the model had malfunctioned. They said that certain region selections were suspicious, but they were uncertain on whether they should act on this and revert to manual or not. Was this a normal thing or was this a malfunction? In practice, this ambiguity would need to be resolved. Finally, users established trust progressively. Many mentioned that they were initially skeptic to the system, but after going through negatives again and again with increased sensitivity, they never found anything, and eventually stopped increasing the sensitivity. I believe that providing such a mechanism so users can balance the speed-confidence trade-off is an important idea that could be refined further. In conclusion, I present the Rapid Assistive Visual Search, which is a human AI user interface that manages to increase the speed of reviewing lymph nodes despite using an AI model that performs worse than pathologists. The design effort was not guided by recipes of do's and don'ts, but instead thoughtful consideration of pathologists' work, human factors, and the strengths and limitations of our predictive model. The datasets used are available for extending our work. Thank you!